Hi, I'm Hanglu. I'm going to give you an introduction to left-orderable groups.
So the structure of the talk will be as follows. The talk will be very introductory. In part 1, I'll give you basics and examples. And in part 2, I'll give you an overview of the research. We'll state a lot of results in our research niche in part 2, but we won't give any proof of these results.
So we say that a group is left-orderable if there's a total order on the group such that the order is invariant under left multiplication. So G is smaller than H if and only if F times G is smaller than F times H for all elements G, H, and F in G. So why study left-orderable groups? Let me give you 4 applications. First, there's a large class of groups which are left-orderable. For example, all surface groups except the one for the projective plane are left-orderable. Rags and virtually poly-Z groups are left-orderable. Second, we have a link with dynamics. So for countable group G is left-orderable if and only if it's isomorphic to a subgroup of the set of orientation-preserving homeomorphisms on R. So if you didn't like the definition for left-orderable groups, maybe you can just think of our left-orderable groups as these subgroups. Third, left-orderable groups were used by Minier in a proof of the Hammond-Neumann conjecture. So the conjecture says that if H and K are non-trivial free groups, then the rank of H intersecting K minus 1 is less or equal to the rank of H minus 1 times the rank of K minus 1. And finally, left-orderable groups are related to the zero divisor conjecture, which is famous in the group ring area of study. So let R be a ring without zero divisors and let G be torsion free. Then the conjecture says that the group ring RG has no zero divisors. And what is known is that if G is left-orderable, then RG has no zero divisors. So let's look at a first example. I've rewritten the definition of left-orderable group in case you want to follow along. So the integers with respect to addition has a natural left order, which is given by, well, the left order that you think of. So minus 1 is smaller than 0, smaller than 1, etc. This order is clearly invariant under addition. Now the definition of left order is completely symmetric. So the order 1 is smaller than 0, is smaller than minus 1, smaller than minus 2. That's also another order. So now let's define an equivalent notion, which are positive cones. So we can look at left orders in terms of sets called positive cones. And that way we don't have to keep up with, every element being bigger than another, and we can just look at a set. So roughly speaking, a positive cone is trying to capture the notion of additive positivity into a group. So P is a subset of G, and it's a positive cone if P is closed in a subgroup operation. So you can imagine if you add 2 positive things, you get another positive thing. And also G's partition between positives, inverse of positive, and the identity element, which we call the trichotomy property. So for example, Z with respect to addition emits a positive cone, which are all the positive elements. Now we said that positive cones are an equivalent notion to left-orderable groups, so Z also emits another positive cone, because Z has 2 orders, right? Which is just all the negative elements. Z mod NZ, or any group with torsion, does not emit a positive cone, because suppose that you have a group with torsion, and suppose that that has a positive cone, then there's some elements G, which, such that G to the n is equal to 1, and without loss of generality, G is in P, but that would mean that G to the n is equal to 1, and that's in P by the semigroup closure property. That's a contradiction because 1 cannot be in the positive cone by the trichotomy property. So let's look at our second closure property. But first, let's start with an example. So we know that Z is left-orderable, and actually Z squared is also left-orderable when viewed as Z equals C. So here I've drawn the area for Z squared, which generates AB, where the cyclic group generated by AC and the cyclic group generated by B is Z equals C. Now, a positive cone for Z squared is given by A and BN, where n is positive or n is equal to 0, then m is greater than 0, which is all the green dots in my kilogram. So this is our lexicographic order with leading factor A, where A is just isomorphic with C. And notice that the positive cone that we have drawn here is equal to PAB union PB, where PA and PB are both positive cones of C. So using the positive cones of C, we've constructed our lexicographic order for Z squared. So this idea of composing positive cones generalizes to extensions. So suppose that you have a short exact sequence with n being the kernel and q being the image. N stands for normal and q stands for quotient, with pn and pq being the positive cones of n and q. Now, pqn union pn will be a positive cone for g, and let's prove it. So every element of g can be written as qn, where q is in q and n is in n. To prove trichotomy, notice that the G is such that either Q is in PQ or PQ inverse, or Q is equal to 1, right? And similarly for N, so every element of G is either in PQN or PN, or it's in the inverse of that. Or it's equal to identity if both Q and N is equal to 1. To show certain group closure, if G and H are in the positive cone, then you can write G as Qn, H as Pn, and now you want to multiply them together so that they're in positive. Now GH will be equal to, of course, Qn, Pn, but now we want to shift the P so that it's next to the Q. And what you do is you conjugate the N, and with that, you're going to have that Qn_Pn is equal to Qp inverse and Pn. Now, the N is conjugated, but that's fine because N was in a normal subgroup. And now we have that GH is equal to Qpn prime N. So now we can check that our product is in the positive cone. Well, if G and H weren't in the positive cone, then either Q or P are in PQ, in which case G times H is in P, because if one of them is in PQ, then the other one is either equal to the identity or is in PQ. Or both Q and P is equal to 1, in which case N prime is just N, and both N and N are in Pn. So now G times H is in Pn, so it's in P. So that finishes the proof for the semi-group closure. We're going to call this lexicographic order with leading factor Q. So extensions of left-orderable groups are left-orderable. This already gives us quite a lot, just knowing that Z is left-orderable. So what I mean by that is that now we have that polyzy groups are left-orderable. Recall that G is a polyzy if we have a subnormal series with G naught being G, and in G we have a normal subgroup G1, and in G1 we have another normal subgroup, etc., up to Gn, which is going to be just the identity, such that the quotient of Gi over Gi plus 1 is isomorphic to Z. Now, Z is left-orderable, and extensions of left-orderable groups are left-orderable, so you can do induction on the length of the series to prove that polyzy groups are left-orderable. Moreover, left-orderable groups with a polyzy group as a finite index subgroup, so virtually polyzy subgroups, are polyzy by an application of Morris's theorem. This is going to be in an upcoming paper with Tiago, Cristobal Rivas, and myself. And finally, solvable Wormslark-Solitaire groups are left-orderable. So those groups are written as B1Q and have presentation with two generators, A and B, and one relation, which is that A, B, A inverse is equal to B to the Q, when Q is not equal to 1. So these groups can be viewed as a semi-direct product of periodic rationals and integers, both of which are orderable. Therefore, these groups are orderable. Now let's look at locally indicable groups, which are a large class of left-orderable groups. So a group is locally indicable if for every non-trivial finitely generated subgroup, we have a homomorphism onto Z. It's a well-known fact that locally indicable groups are left-orderable. But the proof of that fact doesn't give us an explicit left order because it relies on the following equivalence. G is left-orderable if and only if for every finite set G1 up to Gn of G, which doesn't contain the identity, we have exponents epsilon I such that 1 is not in the semigroup generated by G1 epsilon 1 up to G1 epsilon n, where those elements that generate the semigroups are just GIs or GIs, right? So now, once we have this equivalence, the EIs can be given by this map onto Z that we have. But next, let's look at the sketch proof of the equivalence and get some intuition as to why using the homomorphisms onto Z we can't get an explicit order. So I've put the equivalence on top just so we can follow along. So let's look at a proof sketch. So the forward direction for the equivalence is very easy because we have the G is left-orderable, and now to choose the right exponents such that you get a finitely generated semigroup which does not contain 1, all you have to do is that you choose the exponents so that the semigroup is contained in a positive column, right? So for each GI, either G or G inverse is in the positive column, so you just choose either G or G inverse to be a generator of your semigroup. The opposite direction is a more interesting one because it says that we have a local to global relation. So we can choose exponents for finite sets of elements of G to form semigroups excluding ones, and since the statement is for every finite set, these sets may grow larger and larger. And you can see the limits of these growing nested sets as positive cones. And more formally, these positive cones will be given by the limit of a sequence of nested sets in the power set of G, which will exist, so the limit will exist by compactness of the power set of G viewed as a Tychonoff space. Therefore, because these limits are given this way, we only know that positive cones exist, but we don't know what they look like. The only thing I want you to remember from this is just that locally indicable implies left-orderable, but no explicit left order is given by the local indicability. So now let's look at some applications of local indicability. First, free groups are left-orderable. The proof is very simple. By the Nielsen-Schreier theorem, every subgroup of a free group is free. In particular, every finitely generated subgroup of a free group is free. And for every finitely generated subgroup, we can get a homomorphism onto Z by sending every generator to 1. Now F is locally indicable and thus left-orderable. Now explicit orders can be given by the Magnus embedding, an action on the real line, an action on the tree. This is a result of the Sunik. But there are in fact uncountably many orders, so feel free to come up with some. Secondly, rags are also left-orderable because they're polyfree. And the length of the series, of the subnormal series, is bounded by the chromatic number of the defining graph. This is a result of Remark and Shinnick. And therefore, rags are left-orderable following the extension theorem.
Now let's talk about surface groups. So surface groups are left-orderable apart from the fundamental proof of the projective plane. And the proof is long and uses a lot of algebraic topology, which I won't explain in this talk due to lack of time, but if you know a fair amount about these surface groups, then this might be relevant to you. So let me sketch this proof for those who can follow this easily, and if not, no big deal. So the proof comes down to the following. Closed surfaces, except for the torus, the projective plane, and the Klein-Body group, so connected sum of two projective planes. Those closed surfaces, except those three things, are all a cover of the connected sum of three projective planes. Now, if you have such a surface, then, by basic theorem in algebraic topology, the fundamental group of S will be a subgroup of the fundamental group of this connected sum of three projective planes. Now, left orders are closed into subgroups, so we will restrict our attention to showing that the fundamental group of the connected sum of three projective planes is left orderable. Now, what you can do is that you can find a cover for this connected sum such that we get a short exact sequence, 1 to the fundamental group of this cover, to the fundamental group of your connected sum, 2z squared to 1, such that the fundamental group of their cover is free and thus left orderable. Now you use the extension lemma to obtain that pi1 of the connected sum of three projective planes is left orderable. So for our last topic, let's talk about the dynamic realization of left orderable groups. So our claims is as follows. For a countable group G, G is left orderable if and only if it's isomorphic to a subgroup of the group of orientation preserving homeomorphisms on R. So let's sketch the proof. For the forward direction, so for the dynamical realization, let T be a map from G to R such that it's injective and such that T preserves the pre-established order in G. So G smaller than H will mean that T of G has to be smaller than T of H. I'm not going to define such a map, but I think it's quite believable that such a map exists. And now once you have such a map, you can define an action of G on T of G equivariantly. So G acting on the point T of H, you will set that to be equal to where G times H is sent to. Now you can extend this action on R minus T of G, so the complement, by defining the action of find me. So if you have X, which is a point between T of G and T of H, then you can write X as a linear combination of T of G and T of H, and now just apply the action linearly. For the opposite direction, you can order group elements by their action on a countable dense set. So suppose that you have F and G that are both acting on R in a orientation preserving way. Then we say that F is smaller than G if and only if F times Xi is smaller than G times Xi for some Xi in the countable dense set, which will be determined as follows. So you have a countable dense set and you can enumerate all the elements in the countable dense set. And now you just pick the first element in the countable dense set such that F and G don't map that element to the same thing, so don't agree on that element. And now if F maps that element to something smaller than G, then you set F to be smaller than G in the group order. So this order is almost lexicographic in some sense. So well done. We're done with all the basics now. And what's left is introducing the research and motivating the research a little bit. So let's start with a remark on finite generation. Recall that
a positive cone for z squared was given by two finitely generated positive cones. PA, which is just a set of positive A's, and PB's, which is just a set of positive B's. And we had that PAB union PB was a positive cone for z squared. So in some sense, it's as easy to know if something is positive in z squared as it was for z. But this positive cone for z squared is not finitely generated. I'm just stating this as a fact right now, but we will prove it later.
And in fact, z squared also inherits an isomorphic positive cone as a subgroup of index 2 in the Klein bottle group, with positive cone that's also finitely generated, and in particular it's generated by A and B. So here I've drawn the K graph for the Klein bottle group. You can check it from this perspective. I've highlighted a rectangle which corresponds to the division for z squared. And in darker green, so the greens are the positive elements in the Klein bottle group, and in darker green you have the positive elements for z squared. And you can check that this positive cone is isomorphic to the positive cone above. This positive cone is inherited from a finitely generated positive cone, but this positive cone is not finitely generated again.
So being finitely generated as a positive cone is not closed in the picking extensions, and it's not closed in the picking finite index subgroups. So the takeaway is that being finitely generated is not a very good property to describe how hard it is to determine whether something is in a positive cone. So our research motivation is to have a good way to describe positive cone complexity. But first, let's prove that z squared really has no finitely generated positive cones, so that we didn't just pick a bad positive cone in the previous examples. It's just that z squared really, there's no way for it to have a finitely generated positive cone. So to do that, we need to look at the topology of the space of left orders. So take L of G to be the space of left orders of G, and recall that a left order is equivalent to a positive cone, so points in L of G are just all positive cones. So, alright, so then all P and L of G are positive cones, and thus subsets of G minus 1. And so L of G is a subset of the power set G minus the identity. Therefore, L of G inherits the natural topology on plus 1 minus 1 to the G minus 1, right? Because this is homomorphic to the power set of G minus 1. And now every element P has cardinality of G minus 1 coordinate that is indexed by elements of G that are not 1. So for example, the coordinate of G of P at G is plus 1 if G is in P, and the coordinate of P at G is minus 1 if G is in the inverse positive cone. For example, L or of Z has 2 points, you can name them P and P prime, and they're defined by whether 1 or minus 1 is an either positive cone. So the coordinate of P at 1, say, will be, say, 1, and the coordinate of P prime at minus 1 will be 1. And this portrays whether you choose 1 or minus 1 to be a positive cone. Now, for the topology of the space, we say that two positive cones are closed in that space if they agree on large balls of group elements based at the identity. So here I drew a picture with the K graph, and I drew some concentric balls based at the identity. And here, P and P prime are in the same neighborhood as defined by the ball B sub 2, because they both agree on B sub 2. Notice that this doesn't mean that they both contain B sub 2, because B sub 2 will have positive and negative elements that are predefined, and that P and P prime just happen to contain all the elements which are preset to be positive in B sub 2. The point is that if P is finitely generated, then for a sufficiently large ball Bn, so say B sub 2, P will be the only positive cone which agrees with itself in B sub 2, because B sub 2 will contain all the generators of P, And so if a positive cone, well, if a ball contains all the generators of a positive cone, it will define a positive cone, and therefore that positive cone will be the only positive cone in the neighborhood defined by the ball. So here I wrote that, well, I need some group containing all the generators inside the ball. We take up half of G, right? And so you really cannot, if you contain all the generators of a positive cone, then you really cannot be a different positive cone because a positive cone is maximum in some sense in G. Okay, so therefore, a finitely generated positive cone will be the only positive cone in its neighborhood, so it's an isolated point. For example, in Z, our two positive cones defined by 1 and minus 1 are isolated because they're finitely generated by 1 and minus 1, and these two positive cones can't agree with each other on a single element. The takeaway from this is just that if P is finitely generated, P is an isolated point. So our claim is that L of Z squared has no isolated points, and thus no finitely generated positive cones. Well, the positive cones of Z squared are defined by half spaces and a choice of orientations. For example, this half space, so we have a slope and we have a choice of orientation, so we take all the points above the slope. Well, this half space represents a point in L of Z squared. And notice that here I drew an irrational slope, but if you had a rational slope, then you would have some points of Z squared falling onto the slope, and then you just pick one side of the slope to be positive, as you do for Z. Okay, so half spaces and choices of orientation represents points in L of Z squared. And you could check that these half spaces are really positive cones because, well, they're clearly closing the symmetry operation. So points in these half spaces are vectors, and so if you add two vectors in those half spaces together, then the resulting vector is still in that half space. And these half spaces will also clearly partition Z squared appropriately. So now a neighborhood of Z squared is a set of all positive cones agreeing on a finite ball, but which do not necessarily point outside of the ball. So here I've drawn a ball of radius 4 with preset positive and negative elements. I've drawn two slopes, and we assume that these slopes agree with the ball on what is positive. So these slopes have a choice of orientation, which is that everything above the slope is in the positive point. And so for this ball, I have two slopes with a choice of orientation, therefore two positive points, which agrees with this ball, but these two slopes are clearly different, and they will clearly disagree outside of this ball on whether an element is positive or negative. Now, this picture is highly non-unique to this ball of radius 4, right? Because for any radius, I can find two slopes, thus two different positive cones, which agree on a ball of that radius. And so for any neighborhood of L of Z squared, I can find at least two different positive cones in it. Well, that means that L of Z squared has no isolated points, and thus Z squared has no finitely generated positive cones. So what we just saw is that Z squared has no finitely generated positive cones, but Z squared is an extension of two groups with finitely generated positive cones, Z equals Z. And Z squared is a subgroup of finite index in a group which has finitely generated positive cones. And in fact, you find that the group has only finitely generated positive cones, just like C has only finitely generated positive clones. And therefore, finite generation doesn't capture positive clone complexity well. Our research motivation is to have a good way to describe positive clone complexity. And to do so, we study positive clones in regular languages.
So first of all, what's a positive clone language? So suppose that G is finitely generated, and let X star be the set of all the words over X. A language is a subset L over all the words in X, and the elements of L are called words. Makes sense, right? So a language is just a collection of words over some alphabet. Now we say that L evaluates to P if there's an evaluation map from X star, so all the words of X, to G, such that pi of L is equal to P. So right, so you have words over the generators of G, which map to G. So for example, X inverse maps to 1. And we just want a collection of words which map to P. Now if P is a positive clone, we call L a positive clone language. So what's a regular language? So a regular language is a language accepted by a finite set automaton. And finite set automata capture the idea of needing finite meaning. For example, this automaton accepts the language of binary strings with an odd number of zeros. So here you start at the start state, which is the state on the left, which has the arrow from nowhere leading to it. And you say, okay, well, I'm remembering that I have an even number of zeros. So if I start inputting a 1 as a first leg of my word, then I still have an even number of zeros. But for example, if my second letter is a 0, then now I have an odd number of zeros. So I go to the state with double circle, which is an accept state. Now, if your word was only 1 0, then at this point you would accept it, and so you say that 1 0 is part of your language. However, if you have more letters to a word, then you continue inputting. So if you input more ones, then you stay at the state with the 0. So that's why you have an arrow from 1 pointing to the state itself. But now if you have another 0, then you go back to remembering that you had an even number of zeros. And now you can input more ones, but that's not going to change that. And so that's what a finite set automaton is. So basically it's just all the words that you read, which go from the start state to the final state, with the help of the labeled arrows, and all the words which lead to the final state are the accepted language. So examples of accepted strings would be 1 0, as you said, 0 0 0, and 0 1. And you can check that just by following the arrows. Non-examples would be the empty word 1 0 0. And regular languages are the simplest languages in a classification of languages called the Chomsky hierarchy. So here, I just wanted to show you that a positive clone for Z squared can be represented as a regular language. So here we have a P and PB, and we have a P of Z squared with PAB and PB, where PA is just positive A's and PB is just positive B's, right? And you can see here an automaton that accepts only positive A's, an automaton that accepts only positive B's, an automaton for B, which is just all the words of the B inverse, and then PAB and PB is just a combination of these automatons on the top. So an important point to highlight is that when L represents P, we only need that for every positive element in P, there exists at least one word of L such that the evaluation of that word is equal to G. For example, we know automaton for Z, PA. PA admits a positive language given by A to the N, where N is positive. So A squared A inverse is not in this regular language for PA, even though it represents a positive element. This is very different from the word problem, which is about the pre-image language of the identity. So all the words map into the identity. Yet positive cone languages are related to the word problem, since if W is in a positive cone language, then clearly it doesn't equate to 1, because it got something in P, which is the string blue, and therefore W is not indicable. So here's a lemma. If G is such that the pre-image language of one of its positive and is regular, then G is trivial. So this justifies why we have such a definition for our languages evaluating to P, why we only require one word represents each element that's positive, because if we had the whole pre-image language being regular, then it's trivial, so we wouldn't want to study that.
So now let's look at some closure properties of regular positive cones. So this is part of my research overview, and I won't prove any results in this last section of our talk. So first, regular positive cones are closed under extensions. The proof is really easy, and if you follow carefully what we did in our example of the positive cone for z-squared, the proof is essentially the same. Second, regular positive cones are closed in finite index subgroups. This is again a property that we wanted, and this result can be seen in my first paper. Third, having a regular positive cone is independent of generating sets, assuming that the sets are finite. This is a known fact and is easy to prove. However, being regular is a positive cone dependent property. So for the same group, some positive cones make it easier to figure out if an element is positive in it or not. As an example of that, we have the group B1Q, so the bomb source solitaire group with parameter 1 in Q, where Q is greater than 1. This group has both regular and non-regular positive cones, and this is shown in my upcoming paper with diagrams and indicability. So regular positive cones have very nice geometric property. So here's the definition. A set P of G is coarsely connected if it's connected in the K graph for some R neighborhood. So think of your set in the K graph and thicken it by R. And if that set is connected, then your original set is coarsely connected. Now, regular positive cones are coarsely connected. This is a result of Alonso and Sarah Rivas. And this is very interesting because a priori, regular positive cones, like being regular, is a computational property, and it's a measure of how difficult it is to figure out if some element is positive relative to the positive cone in your group. But being coarsely connected is purely geometrical, so it's maybe not so obvious how you get from one to the other. But actually the proof of that is fairly straightforward, and your R will be given by the number of states in the finite set automaton accepting language representing the positive cone. Here's an application of this. So first, non-abelian free groups have no coarsely connected positive cones, and hyperbolic groups with coarsely connected positive cones. So maybe think of hyperbolic groups in this case as thickened abelian free groups. So okay, if you thicken your abelian free groups, then you can get some coarsely connected positive cones, but these positive cones would have to be very distorted in the sense of not being connected by quasi-geodesics. This is again a result of Alonso, Anderlin, and Crystal Vargas. Now, relatedly, free products, which are sort of a generalization of free groups, those have no regular positive cones. So that's a weaker statement than saying no coarsely connected positive cones, but on a bigger set.
right? And this is a result of Suzanne Hernier and Zoran Schilik. And also as an analogy to the hyperbolic group in thickened free group thing, asymmetric hyperbolic groups, which are a generalization of hyperbolic groups, well, we don't know if they have closely connected positive cones, but we know that they have no regular quasi-geodesic positive cones. And this is a result in the first paper. Now, for a last interesting topic that I want to introduce here, let's look at crossing left-orderable groups with Z. So something inherent about positive cones change when you cross groups with Z. For example, let A and B be left-orderable, then the free product of A and B has no isolated orders. This is proven in a textbook written by the Navas and Rivas. And so in particular, F2 has no isolated orders. However, F2 plus Z has both isolated and non-isolated orders. This was proven by Katie Mann and Cristobal Rivas. Moreover, F2 cross Z has a finitely generated positive cone, which is part of a new family of groups with K finitely generated positive cones for any K greater or equal to 3. This was a result in my first paper, and this was interesting because whether such a family existed was a question left open by Navas in 2011. In general, free products of groups with regular positive cones, like that as A free product B, those have a one-counter order. This is a result of Dixon-Schilik, and one-counter orders are just like one level of complexity above regular positive cones in this hierarchy of complexity called the Chomsky hierarchy. And this is really the best you can do because Hernier and Schilik have proved that free products have no regular orders. Lastly, if you take the free product A and B of two groups with regular orders and you cross that with Z, well now that has a regular order. This is a proof that's given in our upcoming paper with Jabin and Cristobal Rivas. And the proof basically relies on using UZ as a counter.
So we've reached the end. Thank you so much for listening, and I hope this was interesting. I personally learned a lot preparing for this talk.